We are going to have a brief discussion on minor 1 problems and then we continue with differential amplifiers. Before we take the minor 1 problems, the business of a common mode operation of the differential amplifier is output impedance. This had posed a problem. Apparently you have not tried. I should have left it to you, but for the benefit of recording, let me tell you what the trick is. This is the equivalent circuit, R sub C, okay? And in order to find out the output impedance, what we are going to do is to connect a voltage source here, V, and find out the current I, okay, with the input voltage source short circuited. That means this comes to ground, okay. That's it. If I find V by I, then I'll know what now this is V pi. I will know, oh, there was something else, RS. That's right, I forgot about that. RS has to be brought in. Now if I draw this circuit in a little is the point clear? Yes. What we are trying to find out is this, and the question was, I had claimed that it's equal to RC. There was objection from the class because there is another current GMV pi, but you will see the trick, what happens. V and I will draw the circuit in a slightly different manner. There is an R sub C, there is an R sub C, this is grounded. Then you have GMV pi, you have two resistances, one is twice REE and the other is R pi. I won't combine them because then I will lose V pi with this polarity plus minus and then NRS. Alright. Now what is the current through R pi? Obviously this current goes up, equals to V pi by R pi. Agreed? So what is the voltage across this? This will be V pi, then one plus RS by R pi with this polarity, minus, no, plus and minus. Agreed? This is the voltage. So now you can write a node equation at this node. What is the node equation? All the currents coming in should add to 0. So GMV pi, this is one current, plus V pi by R pi, okay, plus this voltage by 2 REE. So V pi 1 plus RS divided by R pi divided by twice REE, this should be equal to 0. Is that point clear? We have not assumed a voltage across GMV pi. We don't have to. We write a KCL. Now in this equation, what is the variable? Variable is V pi. And this equation should be true for all values of R pi, RS and REE. So what is the solution? V pi equal to 0. Which means, I beg your pardon? Please repeat. Okay, in this equation, we are trying to find this voltage V pi. Okay, V pi is the unknown. And these are constants, RS, R pi, REE. And therefore, the only possibility is that V pi shall be equal to 0. Which means that there is no current here. And therefore, the output impedance is indeed R sub C. Do you see the trick?
Yes, sir.
It is a hidden value. Even though the circuit looks complicated, the output impedance is very simple. We shall get another example of this in maybe in the next class. Another example of such complicated things, but ultimately the voltage is 0. Yes.
What's the trick in that? So it's directly coming from the equation.
Trick is, I saw this. You have to observe, not just see. I observed that all currents coming here depend on V pi only, nothing else, and therefore the sum of all these currents equal to 0 will mean V pi equal to 0. I don't have to write all these equations. That's the trick. Yes.
So what happens if we consider R0, small R0?
What happens if we consider small r0? Then the situation is quite different. Then the situation is quite different. Then you have to have V minus this voltage divided by R0. Therefore, V will come into the picture. If R0 is there, then all this simplification vanishes. And life becomes a little more uncomfortable. Okay. Any other question?
Sir,
Yes.
why can't we take the impedance to be infinite directly?
Which impedance?
GMB, the current source, we get directly.
No, we may not, because if this current depends on V, if this current, for example, if we have an R0 in parallel, then there is a problem. You see, if V pi depends on V, then there is a problem. This is not an independent source, it is a dependent source. So we cannot take this as 0, because then there will be a current drawn from here. Okay, now about minor 1 problems. Since the people who will be watching the film did not take minor 1, I have to repeat the question. Question 1 was 11.2 volt, 21K. Then we have a current mirror, Q2, the base and collector are connected. Then you have Q1, which is connected here. There is in addition a resistance R sub B. This is the only difference between the ordinary current mirror and the question that I had set. And this is R sub C, and then connected here, and this voltage is VCE1 plus minus. The question that was asked for is to determine I sub R, this current is I sub R, then I sub C2 and I sub C1. Determine these as functions of RB, because RB has come into the picture. Find out these 3 currents IR, IC2 and IC1 as functions of RB, and show how they vary with RB by means of a sketch. Then determine RB in order that I sub C1 is equal to IR by 2. Obviously, this question itself shows that this current, which normally should be equal to IR, is now being controlled by R sub B. This current can be as low as half of this value by appropriately choosing R sub B, and that is very obvious that R sub B draws a current. In addition to IB1 and IB2, there is an IB through R sub B, and therefore R sub B controls the current. And under this condition, under this condition you have to find out, no, VCE1 is 6 volt, so you have to find out what is R sub C. If VCE1 equal to 6 volt, you have to find out R sub C. The solution should be obvious. That first is that I sub R is obviously the power supply 11.2 minus VBE1 or VBE2, because the two are equal, 0.7 divided by 21K, which is equal to 0.5 milliampere, and this is independent of RB. On the other hand, on the other hand, 0.5 milliampere, that is this IR, if I write KCL at this node, okay, KCL at this node, this would be equal to first I sub C2 plus I sub C1, no, I sub B1 plus I sub B2 plus IB, which is equal to 0.7 divided by RB. Okay, 0.7 divided by RB. Now these two are equal because the bases are tied together, and therefore I can write this as I sub, what about IC2 and IC1? They should also be equal. So I can write this as I sub C1 1 plus 2 by beta, agreed, plus 0.7 divided by RB, from which I get I sub C1 as equal to 0.5 milliampere minus 0.7 divided by R sub B divided by beta has been given as 200. So 2 by 200 is 0.01, so it is 1.01, and this is also equal to I sub C2. Obviously this sketch would be, where would it start from? If I plot IC1 and IC2, the maximum value obviously is 0.5 divided by 1.01 milliampere. This occurs when RB is infinity. Can we start from RB equal to 0? No. We must start from a non-zero small value such that the voltage can be maintained at 0.7, which we have not asked you to determine, but it is possible to determine. So do not start at RB equal to 0. At RB equal to infinity, the curve goes towards 0.5 divided by 1.01 milliampere. Okay?
Excuse me, sir.
Yes.
So if we take, sir, RB equal to 0, sir, it's a short circuit.
So
So current is 0,
0.7.
sir.
Pardon me?
So the current would be 0, sir. IC would be 0.
No, but the
Because
transistor
it is
does.
not being said that the transistor should be in active region, sir. This is not specified, sir.
Then all this calculation will vanish. That 0.7.
But sir, it would be IC would be 0, sir, if there is a short circuit.
If it is short circuit, there cannot be a current. Yes.
Yes.
Correct. VBE. That's right. Exponential this minus 1, that would be
It would
equal
be
to 0.
0.
Yeah. Okay. IC1 would be equal to 0 when RB equal to 0.
Yes, sir.
Okay. Wonderful. So we can start from here. Agreed, all of you? Okay. I will, however, leave this a little dotted line here, little dots, because this question, the region is a bit uncertain. When actually it goes into the active region, you are quite correct that if it is perfect short circuit, then the current has to be 0. Because VBE equal to 0, exponential VBE by VT is 1, that minus 1 is equal to 0. That is perfectly all right.
The
Okay?
nature of the curve will be different in this region.
Nature of the curve would be different in this region, yes.
So,
You shall
the
have.
basis of the assumption is VB is 0.7. Nowhere in the question it was given that it's a silicon transistor.
Oh, we assume that it is silicon, and you can assume a germanium, we will give you full credit.
So I have used the diode equation instead of VB, and then I've done the whole calculation.
That we will see.
Sir, in that case, IR will also matter.
Yeah.
Because for RB equal to
IR will also
IR
change.
will not be equal to.
That is correct. That is correct. The whole calculation will fall to the ground. Okay. The other question was, what is the value, what value of RB is required for IC1 equal to IR by 2? So what you do is put 0.5 divided by 1.01 milliampere minus 0.7 divided by 1.01 RB is equal to 0.25 milliampere, and find out RB. That's very simple. And the other condition is that VCE1 has to be equal to 6 volt. If VCE1 is 6 volt, this means that 11.2 minus R sub C into 0.25 milliampere. This is VCE1. this has to be 6 volt, and therefore find out R sub C. These are not problems. Any question on question 1? Question 2. Question 2 is requires keeping your eyes and ears open. All right, let me draw this circuit. There is a C1 Vs, then 100K, 100K, then you have two transistors in what is called a Darlington connection, Q1, Q2, a Darlington connection. This is 1K, and you have 10K, then this goes to plus 6 volt. The output is taken from here, C2, this is V0. Oh no, I made a mistake. Oh, this is also, I'm sorry. No, there is a capacitor. There is a 10K here. Oh, this is not there. Made a mess. Anyway, this connection is not there. This is connected. Q1 and Q2 collectors are connected. There is a capacitor, and this is 10K. Okay. The question was draw the mid-band equivalent circuit of the amplifier shown below with numerical values of components. That is R pi, GM, and everything has to be calculated numerically. Only the equivalent circuit, no calculations were needed, and Rx1 and Rx2 were to be ignored. The data given was beta 1 equal to beta 2 equal to 100. VA1, the two early voltages are also equal, 150 volt, and VBE1 is equal to VBE2 for calculation, assume them to be 0.7 volt. The point of this example, suppose we draw the equivalent circuit blindly. Let's see what the equivalent circuit will look like. Then we will come to the actual intricacies of the problem. The mid-band equivalent circuit will obviously be Vs 10K, C1 is a short, 100K and 100K in parallel gives 50K. Then from here, from the base to emitter 1 is R pi 1, this is V pi 1, this is E1 and B2, emitter 1 and base 2. Okay. Now from the collector, collectors are also common, C1 and C2 are connected together. So from the collector you have a GM1 V pi 1, the current source, and R01, okay. From here, from B2 you have, from B2 to E2 you have an R pi 2, this is E2, and this voltage is V pi 2 plus minus. Then from E2 goes to ground at 1K, alright. Then go to collector 2, C2. From C2 to emitter to E2 you shall have GM V pi 2, GM2 V pi 2, agreed. This will come, and in parallel with this will come R02. What else do we have? We have an RC which is 10K, and this is my V0. This is the equivalent circuit. Very simple. Equivalent circuit drawing is not complicated, and we can find out all the parameters if we know the currents, IC1 and IC2, and that's where the problem lies. The current can be, let's start from the Q1 end. You see that 6 volt divides into 200K, so 3 volt is the equivalent voltage that should be equal to 50K multiplied by IB1, okay, plus VBE1 which is 0.7 plus VBE2 which is 0.7 plus the drop in 1K, okay. We are going from here to here, here to here, and then drop in 1K. Now 1K drop would be, the current would be 1 plus beta 2 times IB2, which is 1 plus beta 1 IB1 multiplied by 1K. And beta 1 and beta 2 are given to be 100, and therefore this equation can be solved, and my solution had come out to be how much? 0.16 microampere. If this is 0.16 microampere, then obviously IC1, which is 100 times this, is 1.16 microamperes, okay, multiplied by 100, 0.016 milliamperes, okay. And I sub C2, I have not multiplied by 101, it would have been slightly different, multiplied by 100. If I multiply this by 100, then this comes as 1.6 milliampere, and that is where the complete problem fails. You see, if IC2 is 1.6 milliampere, then the drop in 10K should be 16 volts, and the drop in 1K has to be 1.6 volts. So 17.6 volts is the minimum VCC that we need, but the VCC given was plus 6 volt only, and therefore the conclusion is that Q2 goes into saturation, and the equivalent circuit in terms of GM, R pi and R0 is no longer valid, and therefore the equivalent circuit is valid only up to the output of the first transistor. The rest of it is not valid. There is an equivalent circuit in terms of a diode which maintains a voltage of 0.2 across the collector to emitter. You can still calculate the currents by assuming this voltage to be 0.2. The rest of it is dropped in 10K and 1K, and therefore you can find the current. The base obviously is overdriven. The current that will flow now in IC2, if you divide that by beta, it would be much less than what actually comes here, that is 1 plus beta 1 IB1. And if you had recognized this point, I'd give you full credit, but if you have not, if you have drawn it blindly, I have also been generous and asked Mr. Joshi to give you full credit. You don't expect it in the final, you must be able to recognize this. A few people recognize this. I don't know whether in the minor paper or outside the minor paper. Outside. But anyway, I appreciate that. That is what I said, that you have to keep your ears and eyes open. About the third problem. The third problem was a common base amplifier, and the question is this: Vs plus minus, then you have a common base, so a capacitor, bypass capacitor, a resistance R sub 2, a resistance R sub 1, R sub C, this is plus VCC, and the output is taken here as RL. This is V0. The question was to draw the high frequency equivalent circuit of this and show that AVS is of the form AVS0 over 1 plus j omega by omega 1 times 1 plus j omega by omega 2. That was the question, show. Now, here one has to be careful about drawing the equivalent circuit. Okay? The equivalent circuit, if I proceed step by step, I have an RS, then from emitter to base is connected to ground, so this is R pi, and V pi would now be of this polarity, minus, plus, minus. Okay? This fact has to be recognized. Many people didn't recognize it. I graded question number 3, so I know many people didn't recognize it. So they wrote this current is Vs minus V pi by Rs. Obviously that is a Himalayan mistake. Okay? Then what do we have? From emitter 1, we have a Gm V pi. Now, here comes the question of simplification. Should you recognize R naught or not? Okay? Well, suppose you do. Suppose you do. Many people have also recognized this C naught, despite my saying that C naught mainly is contributed by stray, and stray should occur at the output, not across GMV pi. Nevertheless, let's grant it that they include a C naught, which is the small, very small device capacitance. Okay, let's grant it. Then this is the collector, and the collector goes to R sub C. What else? RL, and this is V0. Is this the equivalent circuit? Where is C mu? From the collector to base. And there is no reason why you cannot include R mu also, because fortunately they come in parallel. Where is C pi? Okay, good. There is a C pi also. Alright. Now, the problem is obviously this combination R0 C0. There is no other problem. But suppose this can be combined into a single resistance RL prime. Okay. Now, will there be 3 critical frequencies or 2 critical frequencies? Is the house divided between 3 and 2?
It should be 3.
We neglected one.
You got 3. You got it wrongly then. Okay. If I write, it should be 2. I'll tell you. Can you tell me the reason why it should be 2?
Because these 3 capacitors are coming into the one circuit, sir.
One loop.
One loop, sir.
Which means that the voltages are not independent of each other. You see, if I write a KVL around this loop, voltage across C0 plus voltage across C pi plus voltage across C mu should be equal to 0. Which means, this is a fundamental thing of circuit theory. This means that these 3 capacitors are not independent of each other. And therefore, you shall get only 2 critical frequencies. If you have got 3, then you have got it wrongly or you have not been able to simplify. That's it. Okay, 3 capacitors forming a loop is equivalent to 2 capacitors. That is 2 dynamic states, not 3. Similarly, if you have a number of inductors connected at a common node, then the degrees of freedom is reduced by 1. If you have 3 inductors connected to a common node, the state of the system or the dynamics of the system will be governed by a second order differential equation, not a third order. Similarly here it would be a second order differential equation. So you have only 2 critical frequencies. Now if you ignore R0 and C0, then these critical frequencies can be obtained explicitly. On the other hand, if you do not ignore R0 and C0, then you get a quadratic which you have to solve for omega 1 and omega 2. But if you had left it as a quadratic and say that omega 1 and omega 2 are the 2 roots of this equation, I have given you full credit. there are 2 or 3 people whom I have given 12 out of 12. Was it 12 or 13? 12. I have given 12 out of 12. Even though they had not completed, because they saw the point. They saw the point. Only thing they didn't do was to ignore R0 and C. If you ignore R0 and C0, life becomes very simple. Absolutely simple. Now, I don't blame you if you did not ignore. I have given you full credit. But in practice, if this was required to be designed, then you better do that. Because otherwise you shall require a SPICE program, or you have to write a program, and this writing a program costs engineer time. And after all the exact calculations, you will have to change resistances anyway. So rough approximations would be all right for omega 1, omega 2, and then the question of design. So I will not carry this to the, I will simply give you the approximate result. That is, if I assume Gn much greater than G pi plus Gs, if this is true, and if G0 is assumed to tend to 0, C0 assumed to tend to 0, then AVS0 is approximately equal to RL prime by RS. This result we had derived earlier, AVS0, and omega 1 is approximately equal to Gn by C pi, and omega 2 is approximately equal to 1 over C mu RL prime. These are the final results under these simplifications. The last part of the question, question number 3, was if omega 1 and omega 2 are comparable. Some people asked me during the minor, comparable means they are equal? Comparable and equal are two different terms. If they are identical, why should you use two terms? We call each of you by one name. Of course, your father calls you by some other name, but that's a different story. As far as public is concerned, you are known by one name. Why should we give two names unless they are synonymous? Okay, so comparable means that they are not much different. They are not different by the ratio of 10, 1:10. For an electronics engineer, comparable means 1:3, 1:4. They are all comparable. If they are comparable, then the 3 dB point is neither omega 1 nor omega 2. You have to calculate it exactly, and the equation that gives it is 1 plus omega h squared divided by omega 1 squared multiplied by 1 plus omega h squared divided by omega 2 squared. That should be equal to 2. That's correct. And this gives you a quadratic from which you have to choose one solution. The solution which gives omega h squared as a positive quantity. Okay, that's the only discrimination or only judgment that you have to apply. Any other question on minor 1? Okay, last time we had considered the question of the equivalent impedance offered by a Widlar current source. So we were in the process of drawing its equivalent circuit. The current source was a resistance R, which is the reference resistance, then the Widlar current source. This goes here and this base is tied to another, and there is a resistance of R sub E. This is Q1 and this is Q2, and this is the current I sub C1. You see, we replaced REE of a differential amplifier by this circuit, and therefore it is of interest to know what impedance, what output impedance is offered by Q1. That would be our equivalent REE. Okay, and what was the purpose? Why did we use a current mirror? Because we wanted to increase. Why should we increase REE? To increase the CMRR. And why didn't we increase the lumped resistor? Why did we take help of two transistors?
IC design, we can't use it.
Because in integrated circuits we cannot go beyond a certain resistor, and the absolute limit is 50k. 20k is honored by IC designers as the limit that they can go, but absolute maximum is 50k. And if you increase REE lumped value, we also have to increase what? The power supply, VCC and VEE, which means that there will be much more dissipation in the circuit, and integrated circuits are not designed to withstand heat, okay, because the volume is very small. Now we want to draw the equivalent circuit and find out REE. This is an interesting exercise. What we do is we start from C1, and you see from collector 1 we shall have an R01 to, what is this point? Emitter 1, and we shall have from collector to emitter a current source GM1 V pi 1, alright. Then from the emitter of Q1 we have a resistance R sub E to ground, and from the emitter to the base of transistor 1 B1 we have the resistance R pi 1, and the voltage is V pi 1 with this polarity, plus minus. Agreed? Now B1 is also the same as C2, collector 2. Base 1, base 2 and collector 2 are connected together. So B1 is the same as B2 and C2. So as far as C2 is concerned, we shall have a resistance R02, okay, to ground, because the emitter of emitter of Q2 is grounded, alright, R02, and we shall have a GM2 V pi 2 from C2 to emitter 2. What else do we have? We have an R pi 2, that we must have, R pi 2, and the voltage is V pi 2. Which polarity? Plus up or plus down? Plus up, okay. This polarity, this is B2. In addition, we have ignored something else. RX we have ignored completely, but there is something, pardon me? Capital R, which will come from C2 to ground, and therefore capital R comes here. Now here is some observation needed. The observation is that if we look from here, all of them are equivalent to a single resistance, because V pi 2 is the voltage across GM to V pi 2. So what is its what the equivalent impedance is 1 by GM2, and therefore if we call this resistance as R1, it is simply R pi 2 parallel R parallel 1 by GM2 parallel R02. Agreed? So this whole thing can be replaced by a single resistance, and obviously 1 by GM2 is a small resistance, right? This is being combined with R pi 2. Now since beta is much greater than 1, what is this combination R pi 2 parallel GM2? Approximately 1 by GM2. This is a small resistance which is being parallel to R02, so we can ignore that, and capital R we can ignore that also, and therefore R1 shall be a very small resistance and it tends to 0. The other reason is, suppose, now where does R1 connect to? R1 comes in series with R pi 1, isn't it right? Now if R1 was comparable with R pi 1, obviously we could not ignore it, but can we show that R1 is much less than R pi 1? Let's look at this circuit. IC1 and IC2, what is their relationship? Which one is greater?
IC1.
IC2. IC1 is much less because its VBE1 is less than this by this drop, and therefore IC1 is usually much less than IC2. In the example that we took, 50 microampere, and this was 1.43 milliampere. Okay. Now, if the currents are different, what about their GMs? No, what about their R pi's? R pi is beta by GM, which means that R pi would be proportional to
1 by IC.
1 by IC. R pi would be proportional to 1 by IC. And since IC1 is much less,
So R pi 1 is much greater than R pi 2.
R pi 1 would be much greater than R pi 2, which means that we are quite justified in assuming that R1 is far less than R pi 1. So we ignore it. And then the equivalent circuit becomes very simple. R pi 1, V pi 1 plus minus. No, we short circuit this. Okay. And we have a GM1 V pi 1 here, R01, then an RE. We want to find out this resistance. Have we ignored something? We have ignored, of course, R1. That we have made it equal to 0. So what we want to do is to calculate this. So you connect a voltage source here and find the current I. Now you cannot ignore GM1 V pi 1 as having infinite internal impedance because there is an impedance across it, R01. And I urge you to solve this circuit and show that R0 is equal to, I give you the final result only, approximately equal to R01 1 plus GM1 RE. Provided two conditions are valid, that is GM1 if GM1 far greater than 1 by R01 and R pi 1 is much greater compared to RE. If these are true, then the output impedance is this. Now you say R01, what is the order? Meg. Okay? And therefore, the effective output impedance, effective REE, is now of the order of a meg. Not just a meg, it is also enhanced by a factor of GMRE, which can be, let's say, if it is 3, then you have 4 times R01. And what about R01? The current was only 50 microampere. And therefore, VA by R01 will be of the order of a meg. And therefore, capital R0 would be a very large resistance. And there is no op-amp in the world which does not use a current source for its REE. We will stop here.
Modern technology today plays a very important role even in fulfilling our basic needs. No wonder it is usually hailed as the great benefactor of mankind, which promises to usher an era of abundance and thus alleviate all human misery and suffering. The prosperity of the West can primarily be attributed to the widespread use of this technology. Consequently, it seems to be the only solution for multifarious problems of the starving millions of the Third World. Quite naturally, we find all the developing nations of the world, irrespective of their ideologies, going in for massive industrialization. Consequently, today, most of the products used by us in our homes are made in heavy industry. The results of this global industrialization are now slowly becoming evident. Certainly, it has resulted in an increase in the gross national product of most of the countries, but it has also given rise to some very serious maladies. Environmental pollution due to the exhaust of the power plant and toxic industrial effluents, deforestation due to extensive cutting of trees are already becoming a cause for worldwide concern. The increase in inequity in the society and the resulting social strife, the increasing vulnerability to nuclear and other hazards, as demonstrated by the Chernobyl and Bhopal disasters, are also an important consequence of the same technology.
Unfortunately, such is the attraction of the pleasant consequences of modern technology that we are often not prepared to make an objective assessment of the gravity of these problems. We either tend to dismiss these problems as the inevitable price we have to pay for development, or as minor errors or aberrations of judgment which can be corrected by better technology. A closer scrutiny, however, reveals that this is not the case. Most of the achievements of modern technology are accompanied by detrimental effects, often quite serious, and yet we are not prepared to pay any heed to them. This untold story of modern technology forms the theme of this film.
पिछले लगभग 2 वर्षों से जिस समाचार ने भारतीय वस्त्र उद्योग और निर्यातकों को बुरी तरह से झकझोर दिया है, वो है जर्मनी द्वारा एज़ो रंगों पर प्रतिबंध। इस विषय को लेकर जितनी संगोष्ठियां व कार्यशालाएं इतने थोड़े समय में देश में आयोजित की गई हैं, वो स्वयं में एक मिसाल है। शिक्षा संस्थाओं से लेकर सरकारी मंत्रालय और संबंधित उपक्रमों तथा शोध प्रयोगशालाओं से लेकर वस्त्र कर्मियों तक सभी इस चर्चा में संलग्न हैं। आखिर ये उथल-पुथल क्यों? एज़ो रंगों पर प्रतिबंध क्यों? इसका प्रभाव हम पर क्या होगा? इस संबंध में अभी तक क्या कदम उठाए जा चुके हैं? ऐसे ही कई प्रश्नों तथा इस संबंध में लिए गए निर्णय आदि पर प्रकाश डालती है ये लघु फिल्म। हाल ही में जर्मनी में एक कानून पास किया गया, ऑर्डिनेंस ऑन मटेरियल्स एंड आर्टिकल्स, जिसका उद्देश्य है उपभोक्ता की सुरक्षा। आखिर इस कानून से वस्त्र उद्योग का क्या संबंध? संबंध है, इसमें कोई दो राय नहीं कि वस्त्र हर समय हमारे शारीरिक संपर्क में रहते हैं। इनसे यदि किसी प्रकार की हानि होने का अंदेशा हो तो ये कानून निर्माता और वितरक दोनों को आड़े हाथों लेता है। लेकिन आखिर एज़ो रंग ही क्यों? इस सब की शुरुआत करीब 1970 के आसपास हुई। पाया गया कि बेंजीडीन तथा बेंजीडीन आधारित रंग जैसे कॉन्गो रेड के कारखानों में काम करने वाले काफी लोगों के ब्लैडर यानी मूत्राशय में कैंसर के लक्षण थे।
Mechanics is the name of the game. We play with objects, subjecting them to motion under the application of forces. The rules of the game, known as laws of motion, have been derived from extensive studies on the behavior of bodies in nature, from falling apples to the motion of planets in the sky. The laws enable us to analyze the motion of bodies under the application of forces and to estimate the forces for the design of systems to create the desired effects. The action and effect aspects of mechanics applies to deformable bodies, flow of fluids, continuum, and often extended to socio-economic systems. But we will confine ourselves to the mechanics of rigid bodies and point objects, that's particles. It is not the same laws which apply to the entire expanse of size and velocities of bodies. We shall limit ourselves to classical mechanics. Material objects larger than subatomic particles with speed less than, say, 10% the speed of light obey the laws of classical mechanics. Of course, we shall take the state of rest as a special case of motion being zero. Mechanics is at the core of all science and engineering because of its far-reaching applications in high-rise buildings, flyovers and bridges, in the design of electrical machines, in biomechanics and rehabilitation.
Hello. Internet is the name of the game.
What is the internet?
Can I find some courses being offered? Can I seek admission to a university?
I want to read a newspaper.
Can I see what's on in London?
Stock market quotes in Wall Street.
Can we hear music and watch video on the internet?
Can I make a flight reservation to Timbuktu?
Auntie, can I play some new games?
Is it possible to search a job?
Can we attach a file on the email?
Yes, this and many more things can be found on the internet. You don't have to go anywhere. Just relax and surf the internet at your place. Now let me log you into Professor K.L. Kumar.
Why to me, Sangeeta? Let us log in to the internet right away. Here we are, riding high. Let me begin with my home page. Our teaching assignments, the faculty development program, and the consultancies. Let me show you what's new.